Hey everyone, welcome to CS61B's walkthrough video for Spring 2025 Midterm 1, Question 3. My name is Phoenix, and yeah, let's just get into it. So the question states that creating new nodes for consecutive identical elements in a doubly linked list is inefficient. To combat this, 61B Incorporated has created a new data structure called a compressed doubly linked list. Each node in a CDLL has a next and previous pointer along with parameters value and freak, and represents a sequence of freak consecutive elements equal to value. So in other words, if we took the value 5 in this list at this position, we'd expect a freak of the corresponding node to be 3, because if we look at the sublist containing that 5 and all consecutive elements also equal to 5, that length is 3. Similarly, if we look at the node containing this -3 at this position, we'd expect a freak of 2, because the sublist containing that -3 in all consecutive elements also equal to -3 has length 2. And we can see this is exactly lining up with the diagram given in the question. This 5 gets mapped to this node, or I guess it is encoded in this node. You could say this -3 is encoded in this node, or the sublist is encoded in this node. And we can say the same thing about this sublist here, which is encoded in this node. One thing to notice about a CDLL is that if we look at the first parts of its class definition, it looks exactly the same as a doubly linked list. We have a sentinel node and we have a node class, and really the only thing different here is that we have this new frequency parameter that we described earlier. Okay, cool. I think we're ready to move on to the first problem. So in this problem, we're asked to actually write the constructor of a CDLL. And so all these blanks are kind of intimidating me. So I think it's better that we think about how one would do this and then maybe come back and see where we can fit our intuition into the skeleton code. So let's say we have, let's say we have a list -3, -3, 4, 4, and we want to turn this into a CDLL. Well, first let's think about what the CDLL would look like. We'd have a sentinel node. Any doubly linked list has a sentinel node, so any CDLL has a sentinel node. We'd have a node -3. We'd have a node 4. And take a second and pause and try to fill in the blanks here. What would the frequency of these nodes and what would the connections between all these nodes look like? Okay, come back. So because we see the sublist containing -3 has length 2, we'd say this is frequency 2. And same thing with the 4, this would be frequency 2. And then because it's a doubly linked list, we have all these pointers pointing back and forth at each other. This is back at the 4, 4 points back at the sentinel. Okay, cool, but like how do we actually construct this in a systematic way? Well, let's just start with the basics, right? We know any doubly linked list, and so any CDL has a sentinel node, so that's our starting point. And one way we can start constructing this linked list is by just iterating through our underlying original list. And so we'll create a node called -3. So maybe I'll indicate that we're starting at this -3 here. And every time we make a new node, we have to do some kind of bookkeeping where we have to update the sentinel's next pointer. Or I suppose we would start at the sentinel, and so we'd update, maybe we call this pointer cur, right? Cur is pointing initially to the sentinel, and so we update its next to be this -3. And then any new node will have to point back to the previous node we were just at, so it'll point back to that. And we don't know what the next node is right now, so we'll just leave it blank. And then obviously, it'll have frequency 1, since that's the most amount of -3s we've seen so far. Okay, then we'll move to the next position in our list. Well, we see a -3 again. Our current node's value is also -3, so we'll just increment its frequency. Okay, then we'll move on. We see 4, but 4 doesn't match the value of our current node. So we'll make a new node. We'll do all the bookkeeping with like adjusting the pointers. So this will have to point to 4. 4 will have to point back to our old current node. And now we'll consider this to be our current node with a frequency of 1. And then finally, we move on to the last element of this list. we see that 4 has the same value as our current node, so we'll just increment the frequency once more. And then we hit the end of our list, and now we're in sort of the end game. Now we just have to make sure that this fits this. So what we have to do is point our last element, or I guess our current node, all the way back to 4, or all the way back to the sentinel, and then just have the sentinel point back to this current node, this last node that we made. Okay, so putting it all together, all we did is we started off with the sentinel node. We started iterating through our list, adding nodes to it. Every time we saw an element in our list which matched the value of our current node, all we did was increment the frequency of that node. And once we got to the end of our list, all we did was just change 2 pointers. So we set this pointer to be the sentinel, and the sentinel's pointer, or previous pointer, to point back to the current node. So let's see how we can implement this idea programmatically. So let's go back up to our code here. Here we go. Cool. So we see a for loop, and before we were trying to iterate through a list. So I mean, this is as good a time as ever to iterate through the list. So we know we'll be iterating through the elements of this original list here. And we know the type of elements that the original list contains are integers. So we'll call it capital integer. And maybe this is, let's say, a val, right? Or it's some element in the list. Okay, and now our two cases were, well, if the element matches our current element's value, then all we have to do is increment the frequency, right? So it's more likely to be this case here. So maybe we'll say if val is equal to the current node's value, well, then all we have to do is increment the current node's frequency. Now, take a second and try to think about where this could go wrong. In particular, think about the initial case when cur is equal to sentinel. Okay, so maybe consider the list -1 and then 2. So starting off, our val will be set to -1, and then initially, -1, well, what's cur.val? Well, cur.val is sentinel.val. Sentinel.val is this right here, which is -1. So we have -1 is equal to -1, which is true. So then we'll increment, forgot to put the increment sign here, cur.frequency, which is just sentinel.frequency. But this is a problem because we know that sentinel is a dummy node. It doesn't really encode anything about our list, right? It's just there to make our lives easier. And so if we're associating this element of -1 with a node that otherwise we don't really, we don't externally acknowledge, then there's a problem, right? It's like we're missing something from our list. And so one way we can get around this problem is simply by checking or by ensuring that the current node isn't the sentinel. Because again, if we are associating this element of -1 with the sentinel, then we'll never see that -1 again, essentially. Okay, cool. Now, the other side of the coin, when we were iterating through the list in our example earlier, was the case where the current value is not equal to the value that we are at in the list. In that case, we have to make a new node. So maybe we make a node n. It's going to be equal to a new node. And the parameters or the arguments we pass in are going to be the previous pointer. So remember, the new node always points back at the current node, like we saw earlier. We don't know what the next node will be, so we'll just leave this as null. We'll set the value to be equal to whatever value we're at in the original list. And we'll set the frequency to be 1 because we've only seen one of that value so far. Once we've done that, we can set our current node's next pointer to equal this new node. And then we set our current pointer to be equal to this new node. Cool. So let's just walk through what we have right now. For each value in our list, right? So for each value be in our list looks like this, 1, 2, 3. We're going to say if the value of my current node is equal to that value, all I must do is increment my frequency. Otherwise, I'm going to make a new node and then add that to our linked or to our CDLL. And I'll do all the necessary bookkeeping to make sure the topology of my list looks right, to make sure my list structure looks right. Now, right now, we're at the case where we essentially have, maybe this is what our list looks like, or CDL looks like for the list right here. Okay, these back pointers are already set. This is frequency 1. All we're missing are those connections right here, right? So all we have to do is just say, well, we update the sentinel's previous pointer. That's going to be equal to the current node, which is at this point, this last node in our CDLL. And then we update this the current node's next pointer to be the sentinel. And this ensures we have that nice circular topology to our CLL. And note that you can commute the order of these lines because at the end of the day, they're referring to the same objects, regardless of the order. Cool. Let's move on to the next question. Okay. So in this problem, we're asked to implement a iterator class for the CDLL class. And so let's recall what an iterator actually does. So an iterator lets me walk through my CDLL, right? So maybe my CDLL looks like 3, and then 4, this has frequency 2, 2, blah, 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 right? This points back here. My has an X method will tell me, say I'm at this node, it'll tell me if there's any remaining nodes I can walk to, or I guess any remaining elements I can walk to, right? In this case, the underlying list would be 3, 3, 4, 4, and maybe as I'm iterating, I'm at this point, and my has next will return true if there's another element in this underlying list. So maybe there is, and I move to this one, and then once I'm at this point, there is no next because I've hit the end of the list. My next method actually procures, it obtains that next element in the underlying list. So where do we even start, right? Well, a good place to start is if we're walking through our list, or our list starts at some point, and that's going to be the next node to our sentinel. So it's going to be sentinel dot next. That'll be the very first node in our linked list, and so it'll correspond to the very first element in our underlying list. Now, when does a CDL have a next, when does the underlying list of a CDL have a next element? Well, say we've exhausted all of our, say we've already iterated through the amount of, say this is our list here. Maybe this is 3, this is 2. If we're at 3, and we've exhausted all of our things, all of the 3s in the underlying list, so we've iterated through 3 twice, well then we would go back to our sentinel. And if we hit our sentinel again, we knew surely that we must have exhausted all the elements of the underlying list. So we can say that we have a next element if the current node is not equal to the sentinel node. Okay, cool. But to really solidify that, forgot about that. All right, so I'll be back. Okay. So now moving on, we have to implement our next method now. So one way to think about this So one way to think about this is we need to somehow keep track of how many elements are remaining, uh, how many of the same element is remaining, which is encoded by a node in a CDLL. And to make that concrete, maybe it's best to look at an example. Look at 3, says frequency 2. Look at 4, says frequency 2. And I'm just gonna, for compactness, say these point back at each other in this way. Okay. So say where our current node is 3. Well, we want to know when should we move on in this CDL. Luckily, the skeleton code kind of gives us a hint with this count variable. So if we use count to keep track of how many of the underlying elements that each of these nodes encode, this will this will tell us when we've exhausted all such elements. So maybe 3, 3, 4, 4. This node corresponds to these 3s here. And so count will tell us, well, maybe in count is 1, we're on this element, which means we've already counted one of the elements. When count is 2, we're on this element. And so we've exhausted all the elements. Using this sort of mental model, we can say, well, if the count is ever equal to the frequency of the current node, sorry, the count is equal to the frequency of the current node, then we're done with that node and we need to move on. So then all we do is we say, well, cur is equal to cur.x. And then we'll reset the count, because again, the whole purpose of the count is just to make sure we're not going over the amount of elements that each node encodes in the list. So we'll set count back to 0 because we moved on to a new node in the CDL. So now the rest of the blanks. Well, even if we exhausted all such elements, we still need to return that last element in the underlying list. So maybe we'll set that element to a variable. Maybe we'll call it, should I use val? Yeah, we'll call it val. Is equal to cur.val. There's some crossover here. Okay. And then we'll end up returning that value, regardless of whether we went over our allowed limit. And every time we take a value for which that node encodes, we need to increment our count here. And so if we walk through this code here, we say that the value that we're getting out is equal to the current node's value. We'll say the current node is 3, so we'll set val to be equal to 3. We'll increment the count. If the count is ever equal to 2, we know that we've exhausted all such elements, all such 3s in the underlying list, which means we need to move on to the next node in the CDLL, reset the count, and then return that last 3 in this list.